Welcome to Chemistry classes by Vijay Kumar Sethi, class 11th Chemistry, Unit 4, Chemical Bonding and Molecular Structure. And in this video, we will discuss about polar covalent bond, dipole moment, covalent character in ionic bond, that is Fakans rule. First of all, polarity of bonds, that is polar covalent bond. When covalent bond is formed between two similar atoms, for example H2, O2, Cl2, N2 or F2, the shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei and the bond so formed is called non-polar covalent bond. But when covalent bond is formed between two atoms of different elements, that is heteronuclear molecule or heteroatomic molecule like HF, the shared electron pair between the two atoms gets displaced more towards more electronegative atom, in this case fluorine. The resultant covalent bond is called polar covalent bond. Clear? Simply we can say due to the difference in electronegativity of the bonded atoms, shared pair of electron is more close to the more electronegative atom and that acquire the partial negative charge, and another atom which is less electronegative acquire the partial positive charge, and polarity is developed in a covalent bond. This type of covalent bond is known as polar covalent bond. As a result of polarization, the molecule possesses the dipole moment. Simply we can say polarity is expressed in terms of dipole moment. You can see the non-polar covalent bond, polar covalent bond and ionic bond. In this case, electrons shared equally. In this, electrons shared unequally. Electrons are more close to this more electronegative. That's why it acquired the partial. This delta represents the partial. This is partial negative charge, and this is less electronegative atom acquired the partial positive charge. Okay. And in case of ionic bond, complete transfer of electrons taking place. Okay. Na lost the electron and Cl gain the electron. Dipole moment. The product of the magnitude of the charge and the distance between the centers of positive and negative charge is known as dipole moment. It is usually designated by a Greek letter mu. Okay, this is just like this one is mu. Okay, you can say this is mu. Mathematically, dipole moment, that is mu, is equal to charge, which is represented by Q, into distance of separation, that is R, Q into R. And dipole moment is usually expressed in debye units. Debye is the unit of dipole moment and its symbol is capital D. 1 debye is equal to 3.33564 into 10 to the power minus 30 coulomb meter. C is the coulomb, M is the meter. Dipole moment is a vector quantity. Now what is the meaning of vector? That is have magnitude as well as direction. And by convention it is depicted by a small arrow with tail on the negative center and head pointing towards the positive center. Okay. But in chemistry, remember, in chemistry, presence of dipole moment is represented by the crossed arrow. Now, what is this crossed arrow? This one. This is the arrow. Okay. And this is crossed arrow. Put on Lewis structure of the molecule. The cross is on positive end and arrowhead is on negative end, like this. This fluorine is more electronegative, that's why this head is there and this cross is on hydrogen. This arrow symbolizes the direction of the shift of electron density in the molecule. Simply we can say this arrow indicates that electron density is more towards this fluorine. Okay. Dipole moment and geometry. Dear student, if we know the dipole moment, we can predict its geometry. And if we know the geometry, we can predict its dipole moment. Okay, both are related to each other. In case of polyatomic molecules, the dipole moment of individual bond is known as bond dipole. Okay, that's why in case of polyatomic molecules, the dipole moment depends not only on bond dipoles but also on the spatial means space arrangement of various bonds in the molecule, and the spatial arrangement of the bonds in various molecules, this describes the geometry or shape of the molecule. That's why we can say in case of polyatomic molecule, dipole moment is depend on bond dipole as well as on geometry of the molecule. In such case, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. For example, H2 water molecule. This is bent, bond angle of 104.5 degree, and its net dipole moment is 1.85 dB. It is the resultant of the dipole moments, or we can say bond dipoles of two OH bonds. You can see the arrangement of bond dipole in water molecule. Oxygen is more electronegative. That's why this is cross arrow is directed towards oxygen. Okay, and both are in the same direction. That's why resultant dipole moment of oxygen is in this direction. Okay, now there is one question. If you compare the dipole moment of CO2 and H2, both are triatomic molecule. Okay, the dipole moment of this is 0, while this has the value of 1.85 dB. Okay, then how can we explain? For water, we already explained that is water is a bent molecule. That's why it has some dipole moment. But in case of carbon dioxide, actually in carbon dioxide, the bond dipole of both oxygen carbon bonds are oriented in opposite direction like this. That's why they cancel to each other and net dipole moment is 0. We can say that is on the basis of dipole moment, carbon dioxide is a linear molecule. Okay. The dipole moment in case of BeF2 is 0. How can we explain it? This is because the two equal bond dipoles point in opposite directions and cancel the effect of each other. Again, we can say that is BeF2 is a linear molecule. Bond dipole of this BeF bond is directed in this direction, and for this is directed in this direction. They are equal in opposite direction. That's why they cancel to each other, and net dipole moment of BeF2 is 0, and BeF2 is a non-polar molecule. Again, remember, in BeF2, each BeF bond is polar, but as a whole, BeF2 is non-polar. Okay. In BF3, the dipole moment is 0, although the BF bonds are oriented at an angle of 120 degree to one another. The three bond moments give a net sum of 0 as the resultant of any two is equal and opposite to third. This is trigonal planar geometry for BF3. And fluorine is more electronegative than boron. That's why bond dipole of this bond is in this direction. For this is in this direction. For this is in this direction. And the sum of these bond dipoles is in this direction. Okay, that's why this and this both are in opposite and equal. That's why they cancel to each other, and dipole moment or net dipole moment of BF3 is 0. Clear? Now, dipole moment in NH3 and NF3 molecule. Both have pyramidal shape with a lone pair of electrons on nitrogen atom. Now, what is this pyramidal shape? Okay, this is nitrogen, and these are the three bonds. It may be hydrogen in case of NH3, or it may be fluorine in case of NF3, and this is a one lone pair of electron. Okay, this is pyramidal shape. Now, dipole moment of NH3 is greater than that of NF3. For NH3, this is 4.90 into 10 to the power minus 30 coulometer, and for NF3, this is 0.8 into 10 to the power minus 30 coulometer. How can we explain it? First, come to NH3. In case of NH3, nitrogen is more electronegative than hydrogen. And in case of NF3, fluorine is more electronegative than nitrogen. Okay, and these lone pair of electrons present in this orbital, they also contribute in the dipole moment of molecule. In case of NH3, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of the NH bonds. You can see this represent the orbital dipole due to this lone pair of electron. And being nitrogen is more electronegative, that's why bond dipole of all these three bonds are in the same direction and they will add, and that's why net is in this direction. Whereas in NF3, the orbital dipole is in the direction opposite to the resultant dipole moment of the three NF bonds. You can see this is a lone pair of electron. Its bond, we can say that is orbital dipole. This is in this direction, and now fluorine is more electronegative. That's why bond dipole of all these three bonds is opposite to the orbital dipole. That's why they cancel to each other. They cancel somewhat, not completely cancel. They cancel to somewhat, and this is the net dipole moment of NF3, which is smaller than NH3. Okay. Now we have discussed the polarity in covalent bond. That is, covalent bond has some ionic character, some polarity. Now we will discuss covalent character in ionic bond. The cation polarizes the anion, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. We already discussed that in a covalent bond, electron charge density is in between the nuclei in covalent bond. Now, if we consider this ionic bond, this is cation and this is anion. This is formed by the transfer of electron. But in this case, deformation of electron charge cloud of anion, and this is called polarizability of anion, or we can say this electron charge is not completely with this negative ion, that is anion. This is somewhat shared. It is somewhat shared between cation and anion. That's why some covalent characters arise. Now, factors affecting the percent covalent character of the ionic bonds are like this: polarizing power of the cation, polarizability of the anion, and extent of distortion or polarization of anion. Now we will discuss one by one. First one, what is the polarizing power of cation? It is the extent to which a cation can polarize an anion. It is proportional to charge density. Now what is this charge density? This is the ratio of charge to volume. Polarizing power is directly proportional to charge density. More the charge density, greater is the polarizing power for that cation. Now, polarizability of anion. It is the extent to which an anion can be polarized. It can also be called as the ease with which an ion can be polarized. Polarization is the distortion of a spherically symmetric electron cloud to an unsymmetric cloud. In this way, due to polarizing power of cation and polarizability of anion, some partial covalent characters developed in ionic bond. And the partial covalent character of ionic bonds was discussed by Fajans in terms of the following rules, and these rules are known as Fakans rules. First one is size of the ion. The smaller the size of the cation, and the larger the size of the anion, the greater the covalent character of an ionic bond. The charge of cation. Greater the charge on the cation, the greater the covalent character of the ionic bond. Electronic configuration. 4 cations of the same size and charge. The one with electronic configuration like this, N-1 D N NS0. This electronic configuration is typical of transition metals, is more polarizing than the one with the noble gas configuration, that is NH2 and P6, typical of alkali and alkaline earth metal cations. Okay. Thank you student. Subscribe my channel to get the new videos from this chapter.